Okay, let's look at another example. So here we have some kind of an airborne particulate, likely a pollutant, that's measured at 42 randomly chosen industrial workplaces in a region. The mean of all those measurements was 335 parts per million ppm. We're told that we can assume that the standard deviation of the measurements at all such workplaces is 80 parts per million. The EPA considers a level of 300 ppm or below to be safe. Can it be concluded that as a group, industrial workplaces in this region have a level of the pollutant that is higher than what is considered safe? And then we're given a significance level of 0.01. Okay, so the first thing we want to do is we want to write down our sample information. So N equals 42. That's our sample size. And our sample mean, our X bar, is 335 ppm. We are told that we can assume that the population standard deviation, see how it says of all such workplaces. Again, this assumption is not always met, and we're going to talk about in the next section what to do when it's not. So, but for now we've got it, so 80 ppm. And actually this is not a bad place to do to check our assumptions. So remember that our assumptions are, we need to either be able to assume that this particle is normally distributed, or that our sample size is at least 30. And it is. So now let's write down our null and alternative hypotheses. Okay, so our H0 and our HA, or our H1. Okay, so what's our benchmark? Our benchmark is 300 ppm. So our null hypothesis is going to be mu equals 300 ppm. And now for the alternative hypothesis, we need to decide whether it's a one-tailed or a two-tailed test. So we look in our problem and we ask if, when it's asking us about the conclusion, is it steering us in a particular direction? Can it be concluded that as a group, industrial workplaces in this region, so that's our population, have a level of this pollutant that is higher than what is considered safe? Okay, and so the assumption, so that looks to me like a one-tailed test. We should really only be doing that if we have reason to believe it's not going to be the other direction. So what we want to do is, so this is going to give me a mu greater than 300 ppm. Okay, and so this is a good place to also write down our alpha. So what's our alpha? 0.01. Okay, so those are our hypotheses. So now let's sketch our picture. So we sketch our bell-shaped curve. And now we want to we want to shade one end. So which end are we going to shade? The high end, because we have a one-tailed test with greater than 300 ppm. So we're going to put this over here. And so our whole alpha goes into here. So this is going to be alpha equals 0.01. So we get the whole thing instead of cutting it in half like we would for a two-tail test. And now we look at our critical value. So our critical value is going to be Z 0.01. Okay, and so that's that. So now we need to go find our critical value. Okay, so the area to the left of our critical value is 0.99, right? You can write it on your picture if you want. So we get that by taking the 0.01 and subtracting from 1. So what we're going to do is we're going to look up our area .99, 0.99 in our dizzy table. And let's do that. So I'm going to go over to my table. So a couple ways to do this. So we could look up 0.99 in the table. Let's do that first. So 0.99, that's going to be in the positive half of the table. So we want to get as close to an area of 0.99 as we can. So let's see, where am I? 9906, 9904, ooh, 9901 is really close. 9898 is also really close. It's in between, not exactly halfway in between. I guess it's about a third of the way in between, but it's still close enough to in between. I think I'm going to just split the difference. It's a bit of a judgment call. If you use the closest one, that would be a reasonable approach in my viewpoint. Okay, so that means we're going to be halfway in between 2.32 and 2.33, right? And so it's going to be halfway in between these. If you want, you can write them as 2.320 and 2.330, and that makes it easier to see what's halfway in between them. So my critical value is 2.325, or you can just average them. So, but halfway in between 320 and 330 is 325, so that's how I can do it. Okay, so now I'm going to go put that onto my picture. So I just label it. Okay, and so now what we need is our test statistic. Okay, so the first thing we need to do our test statistic is the standard error. Okay, our standard error, that is the standard deviation for all the x bars, which is going to be, and actually I don't need the approximately equal here because this is actually equal. It's going to be sigma over the square root of n. Okay, so that gives me 80 ppm divided by the square root of 42, right? And so it turns out this is approximately 12.344 using your calculator. Okay, so then my test statistic that's going to be my z. So I always subtract what I am comparing. So I take my sample mean and I subtract my benchmark and I divide by that standard error. And so this is going to give me 335 minus 300, that's my benchmark, divided by 12.344. Oops. And so that turns out to be about 2.835. Okay, so now what I'm going to do is I'm going to take that 2.835 and I'm going to go find where it belongs on my picture. And I'm going to look to see if it's in the rejection region or not. So 2.835. Yep, so that is going to be beyond 2.325. So that's going to be over here somewhere. So that is in the rejection region. Okay, so that z equals 2.835. That's in the rejection region. And so what we do is we're going to reject H0, which is part of your conclusion, but that's not enough. We should also write down what we mean in words related to the original problem. And so for here, let's say that this sample does provide evidence that our industrial workplaces in this region have a mean level above 300 parts per million. So something along those lines. Notice we have not said for absolute certain that their mean is above 300, but based on the sample, that seems to be the way the evidences go. Okay, so that is how we would do a hypothesis test. Now notice in both of these examples that we actually knew the population standard deviation. And so think about, is that really going to happen? Are we really going to know the population standard deviation without also knowing the population mean? And so that's something we're going to deal with in our next topic. I hope this helped. See you next time.